Stanford University.
Okay, so welcome to lecture 14 of CS 193G. Today we have Avi Bleweiss from NVIDIA, he is a principal architect in the architecture group. And since being at NVIDIA, he's worked on lots of divergence-rich problems. So he's worked on ray tracing and physics problems, and now artificial intelligence problems. So Avi has a long history in the computing industry. And in graphics in particular, he's worked at HP, SGI, AMD, and now NVIDIA. So please join me in welcoming Avi.
Thank you for the nice intro, Jared. So I guess the title of today is Path Planning System on the GPU. In the context of behavioral simulation, explicit reasoning is often have players abide by a certain set of rules. And to this extent, the underlying functionality much resembles a state machine, and hence the serial nature of the execution. On the other hand, implicit reasoning is something that grants much more autonomy to players or characters and lets them sense the environment. They can make their own decisions by that and then perform an action. This approach seems to be much more scalable. However, it comes with a cost that the underlying tasks are much more compute intensive. But that would appear to be very suitable to the GPU with its single instruction, multiple thread architecture. The title of this discussion is Path Planning, and let me show you a quick demo to illustrate this extent of this work. So what you see here is that there are a couple of dozen agents. They are maneuvering in a closed area from a start to a goal position, and they have to avoid both their peers, contact with their peers, and with the obstacles that appears to be dynamic, and constantly they have to adjust their path to be as optimal as possible. So our domain of interest is what is termed congestion games. And what this entails is that given a player, when he performs an action, he is going to be affected only by those players that perform the same actions. This whole ideology seems like much more high level, much more challenging, but on the other hand, much more promising when it comes to evaluating effective team tasks. On the software side, what we are proposing here is a set of AI libraries where we can offload computational intelligent tasks onto the GPU. This set of library communicates with the planner, and the planner, for this sake, can be a multi-virtual robot system. It could be a game engine, or it could be a synthetic environment module. On the other hand, those libraries communicate with the compute API to the GPU, and the underlying and native for that is Cuda. But the form of the API can be any of Cuda C or C++ or OpenCL or DirectX compute. The other aspect of communicating with the graphics to display the results of AI is done via a very efficient interop in Cuda. So at this stage, we are in a position to formulate the problem. And the problem has two aspects. One is on the design side, which is the planner, and the other one is the simulator, which is more of the implementation. So the first thing that we want to do is to take the configuration space or a level mesh, and what we want to generate out of it is a representation of what is termed a roadmap. And that will guide us throughout the environment. And what we wanted out of it is for it to be very compact and obviously be efficient in the process itself. The second thing is that we want to have the ability to effectively compute a global path that gives a kind of a higher level orientation to agent in an environment. And finally, we want to locally be able to avoid any collision with other character or obstacles that are in the scene. On the simulation side, the important thing here is that AI has to cooperate on the GPU with other entities, like being it a graphics or physics. And we definitely don't want to be in a position where we steal all the resources on the GPU. So we want to use a subset of resources as much as possible. And obviously, what we want to demonstrate at the end of the day, that the solution that we provide on the GPU is scalable enough as we extend the number of players or characters. So our solution is, we decided to adopt a roadmap that is more deterministic, especially within the resolution that it is being composed. We have favored heterogeneous agents on top of something that is more continuous, because we value a lot the idea that you can control a character or an agent individually. This appears to be very important. The underlying algorithm or method that we use for simulation is the velocity obstacles, and I'll talk about it a little later. And of course, in doing our work, we found out that we need to optimize, and I'll talk a little bit about some of the GPU optimizations, namely spatial hashing and nested parallelism. Here is another short clip that I'd like to show you. And what we see here is that there are 4 groups of 100 agents or pedestrians. And as they cross each other on the walkway, you can see that they form a straight lines to avoid collision. And that appears to be something that is known in pedestrian psychology. So for the remainder of my talk, I'll start with highlighting some of the algorithmic aspect of the work. Then we'll go and state some of the challenges of implementation and discuss some design trade-offs. On the result, I primarily am going to show you a comparison between our latest architecture, Fermi, versus the older generation, and see how well AI performs and what Fermi actually brings to the table here. And I will conclude with some limitations, some futures, and some takeaways. So at a higher level, we have formed essentially a 3-piece pipeline of this AI system. At the top level, we have the roadmap construction. And what it takes a description of the configuration space. And we generate out of it a roadmap. Then in the second level, which is the path searching, we take all the agent or characters' goals and goal configurations or positions, and we make an optimal attempt to connect them to the roadmap. Once we have this information in place, then we go and we exercise those agents in a discrete time and simulate them. And for every frame, we issue both a position of the agent and the velocity of the agent. Note also that our system is capable of taking an already pre-built roadmap, bypassing all the roadmap construction stage altogether. So at the roadmap construction stage, what we do is that we take a 3D mesh in, and the first thing that we do is that we voxelize it and we generate a grid. This is actually a binary grid that some cells tells us whether there is an obstacle there or this is a free space. And then once we have that, we apply 2 3-dimensional operators. One is the medial axis transform, and the other one is the distance. The medial axis transform gives us samples in the free space that are a first order of solution to get the most coverage of the configuration space. And the idea behind that is that you add on the distance such that you would want at the end of the day to pick up medial access samples that are the farthest away from obstacles, because they are the ones that are likely to get much more coverage of your space. Once we do so, we go and we apply a modified 3D flat fill algorithm. And what we do in this case is that for every medial access sample, we essentially want to find out whether it covers any free cell in that a priori grid. And once we do so, we mark it as being covered, and we do so for all the medial access samples. Finally, we compute what is termed connectors, and the connectors, what they do is that we add nodes to our generated graph, and those nodes, what they have in them is a crossing of two or more agents that cover the same cell in the grid. The visibility discussion is something that is very common when you do path planning. But in our case, it truly only affects the case where the user provides us with a roadmap. And what this entails is that we do compute two sets of edges. We want to compute all the edges that essentially combine nodes of the graph that are visible, that are unobstructed. And similarly, we do the same thing with agent goals and with every node in the graph. Once we do so, then we run the A-star algorithm that gives us, at the end of the day, an optimal path from every agent goal to every node. And that essentially forms what I termed before the global path. In this discussion, I'm not going to talk about A-star. At the end, there will be an info slide with a paper that I wrote, and you can get all the detailed information there. So velocity obstacle is a well-known and established technique in robotics, and essentially AI people have borrowed it from there. And what it says is that given an obstacle B and an agent A, then the set of velocities VA that at some point in time will cause a collision with obstacle B that moves in a constant velocity VB is the set that we care about in this case. And then, but what people have found is that VO, the velocity obstacle, is a technique that suffers from oscillation. And there is an extension that is termed reciprocal velocity obstacles, RVO, that gets rid of the oscillation and makes agent to reason the same way to avoid collision with each other. So at the end of the day, it takes the average of the velocities of the two agents, and this is the one that would suggest that this is not the velocity that you want to take if you want to avoid collision. And obviously, the complementary set of VO or RVO is the set of velocity that from them we want to choose the velocity. The framework for multi-agent simulation is fairly straightforward. So in our implementation, there is an optional hash stage, and I will talk a little bit later, where we basically build a hash table. And then in the simulate phase, what we do, first we compute a preferred velocity direction for all the agents. And this velocity is something that gives us a foothold in the graph itself. So it can point to either a node in the graph or into the goal position of an agent. Once we are done with it, we go and we compute the proximity scope. And what this entails is that to find out the k nearest neighbors, both agents and obstacles to the agent of concern. And with this, we would try next to find the best velocity to avoid collision with them. Note that we look at only k nearest neighbors. We don't look at the full extent of our environment. this would be a wasteful of computation, because in general, you would want to make your choice or decision based on people that you see, or agent that you see, or agent that you are about to encounter. The next step is to resolve the velocity that we want to have for the next simulation frame. And what we do here is that we sample randomly many velocity direction. They are being bound by a maximum velocity. And what we do there is that we say, if we have an obstacle that is close to an agent, then we will apply VO. And if it is an agent, then we will apply RVO. Once we have iterated all those velocity, then we are in a position to find the one that is optimally close to the preferred velocity that we have computed in a previous stage. Note that here we have opportunity for two levels of parallelism. One is at the outer loop, which is the agent level, and the other one is the inner loop, which is the velocity sample loop, and this is the nested parallelism optimization that I'll refer to a little later. Let's go over the challenges of the implementation. One of the more important aspects for us is that the computation is fairly memory bound. And to this extent, hiding latency in global memory is quite a big task. And it's not just this. It's also that every agent operates on a different, completely, almost randomly path, and which makes threads be highly divergent. And the divergent manifests itself in both having a lot of dynamic flow control, and in addition, referencing in memories in a warp is also can be completely unique for each thread. One aspect that is very critical in that design is that oftentimes in a scenario we don't have more than, say, a few tens of agents. And if we say that an agent constitutes a hardware thread, then that obviously renders the hardware suboptimally. And we would want to have a solution for that such that we can heighten the occupancy of the hardware. And finally, our hash construction right now is being single-threaded and actually being done on the CPU. So that's a limitation because we don't want that to take too much of the frame size. So the resources that we use in our framework, in some cases, they are predictable and we know about them in advance, at least their size, and we can allocate at initialization time. And in other cases, we know the size, but we don't know the data. The data is kind of changing from frame to frame. But there are also other cases, especially in the roadmap construction, where resources are actually dependent. And we only know about them once we have computed a given stage, and then we know how to act upon them or how much to allocate. The type of resources are, some of them are linear in global memory, but many of them are also 3D pitched, and especially for the roadmap construction. In general, we attach a kernel, a Cuda kernel, for each of the computation tasks here, and we have about a dozen of them. If we look at the framework, then you could see that this is essentially a hybrid. The outer loop of simulation is being controlled on the CPU side, and similarly the hash build that is happening every frame. The simulator itself, in its simplified manner, would emit position if it wants to interact with graphics. But then if we introduce a physics engine, then the interaction is slightly different. AI actually emits the velocity that the physics engine have to abide by, and the physics will provide a position that will override any previous position on the AI. And this is on a per frame basis. So I will now highlight some of the design trade-offs that we had for a handful or so pieces in our work. So on the medial access transform, there are like 3 stages, and we have picked the approach where doing a chess distance transform is transferable or comparable to what we have to do with medial access, and that seems to be a very efficient way. But there are still 3 stages to it. One is the distance transform, and then there is a qualification pass that takes the grid that resulted from CDT and gets a qualified binary grid, and then the resolution pass that actually correlates cells of both grids, and whenever there is a true cell on the qualified grid, then we validate essentially the medial access sample. In the serial form, it'll take the time complexity for medial access transform is n cubed, where n is the dimension of the grid. And in our case, we wanted to be very aggressive, and we decided actually to fork or to launch n cubed threads on the hardware. And whenever those number of threads fit the number of threads that the hardware can accommodate, then conceivably we can get to O1 or OK, very close to it. And for the qualify and resolve, this is definitely an O1 type of complexity. On the distant transform, we have picked a generic approach by the reference below that essentially applies a distance transform to a function. And in our case, it's a complete scanline, not just a single voxel. And what is nice in this approach is that their approach is decomposable. So you can run rows, columns, and slices in any order. And the only thing that affects the implementation is that every pass that can start is dependent on the previous pass. So if you do your rows first, columns must wait for the rows. So we have an implicit synchronization going into the hardware. The distant transform is by far less compute intensive compared to the medial access. So in this case, we only launch n square threads, and we get the complexity down to ON. The flat fill, as I mentioned before, is obstacle aware. So it's not the regular flat fill that you know about, where you essentially grow and you override background pixels or voxels without paying attention to anything there. In this case, it is an obstacle aware. So we run essentially a visibility test from every medial access sample to every cell in the grid, and by essentially doing a 3D Bresenham line drawing. And only by that we find out whether this cell is considered for being covered or not. Now, there are 2 approaches that one can take. One is the single voxel, and the other one is the scanline. The nice thing about the single voxel is that if you choose an approach like us, which essentially assumes a private stack, then the single one would consume much more stack. And with the scanline one, you would have much lesser stack space that you would have to need. But it turns out, and this is based on our implementation, we had both implementation going, but the scanline one appears to be much slower than the single. And this is something that we have to still analyze and understand, but it is most likely due to the visibility check that we have to do. So we ended up with the single cell approach, where you can see the pseudocode on the side. So one aspect in this design is that the roadmap and all the data structures that are associated with it can be fairly big. And this is a fairly big footprint that can go to tens and even hundreds of megabytes. So one thing that you want to be careful about, and this is to improve coalescing and as a result memory bandwidth, is you would want to have as good as possible data layout in memory. something that is more thread aligned is the ultimate one. But it's not the case that you can always commit to it or design like this. So one aspect that we have in our design is that we needed to access a list of arrays, and every array is on a variable size. So what we do is that we have a higher level kind of array in global memory, that what it has an offset and a count, and this points to essentially the list of arrays such that we can extract a variable size array, and then from there we can go and iterate. Now there is a downside to it as well, because there is a pointer indirection in this. But this is something that is a good payoff, because usually what we do, we iterate on all the entries of that particular vector, and that amortizes very well this indirection. As I mentioned before, one aspect of the computation is the proximity scope, and we apply a k-nearest neighbor algorithm. Now, the naive approach would be that you would take a given agent and you will compute all the distances with all the agents in the scene, and then at the end you will sort them and you will take the ones that are in this proximity scope or this radial distance from the agent that are of concern. Now, obviously, this has an inherent n-square complexity, but what surprised us most is that throughout this whole process, it actually affected system-level performance. And we realized that this is something that we cannot, it's good to have it, yes, but we would want to optimize that. So we were thinking about KD3, but then looking at the build times for KD3, we thought that this would be too expensive for us to spend within a frame time, and we have decided actually to go with a spatial hash scheme. And the hashing scheme is very simple. What we do is that we essentially compute some random positions within the proximity scope, and what we want to find out is that for every sample we want to find the closest agent to it. And for this we use the spatial hash table. Now, as I mentioned before, there is obviously the runtime benefit for doing hashing is incredible, and to this extent, it is very useful, especially when you run many thousands of agents in an environment. But there is a cost to it, as I mentioned before, and the cost is that you have to build a new a hash table based on the current location of the agent. And this is something that is a challenge in this design. I wanted to talk a little bit about nested parallel. People, when they talk about parallelism, in many cases, this is a flat level of parallelism. So you might take a loop, and you know exactly how to funnel and get threads aligned and get your application or technology going on the GPU. But in this case, we found that actually flat parallel is fairly limiting. And what we wanted to do, we wanted to exploit the opportunity of parallelizing the inner loop of iterating velocity samples. And this is in the simulator. So what we do in this case, so this is another form of execution. We introduce a stage, which is the candidate stage, in between the simulate and the update stage. And for the candidate stage, we launch however many thread grids as the number of agents in the scene. Now, every grid operates on the same kernel, and all the grids, they are disjoint, they have no dependencies, and there is no synchronization between them. Now, what we do in this case is that essentially we do something that is along the lines of a pixel engine in graphics, right? That takes vertices and generates many pixels. In this case, what we do, we take few agents, but we generate so many velocity sample threads, And that leads us to get a better occupancy on the hardware. But one thing to remember here is that there is a data dependency here between the stages. And the grids that are being launched for every agent, they inherit the data of their parent thread, the parent agent. And this is something that we need to take care when we design something like this. So on the velocity threads, so usually, and I'll let you look at some other samples later, there are like hundreds of velocity threads in a given simulation session. So if you come to think about it, if we have something like 16 thread and say 512 velocity samples, then suddenly what we get something like 2K or 4K threads launch as opposed to only launching 16 threads. And this is very meaningful on our hardware. Now, as I mentioned before, the kernel for all those threads is exactly the same. And if you can see, and I don't want you to look at the code itself on the side. This is high-level pseudocode. But you can see that at the end, there is a synchronization statement. And what this synchronization statement entails is that there is, first, what we do a reduce min operation in shared memory. So this is kind of the fine level. But it is the case that we cannot guarantee that velocity sample might exceed the number of threads that are within a single CTA, or they may not necessarily run on the same SM. So then there is another coarse level synchronization that we do across SMs. And in this case, we do a global memory cast. But this is within by far less instances of synchronization. So if we have 512 threads, velocity samples, which are threads in the grid, and we assign 128 threads per CTA, then at most we would need 4 synchronization. And this is the right trade-off in this case. So I will move now to some results. And as I mentioned before, I truly wanted to showcase Fermi architecture in this case. So one thing that I wanted you to look at the table, there is this L1 shared configuration, and probably some of you are familiar with it. So Fermi allows you to actually configure how you partition bytes between shared memory and L1. And you can do it in a 1648K byte type of thing. There is a total of 64K byte. Now, for AI or for our workloads, which are heavily memory bound, we actually gave precedence to L1 in this case. So throughout all our implementation on Fermi, we program Fermi to be configured to 4816. The other thing, if we just look at the clocks and bus widths of the 2 generations that we care about, which is GTX 480 and GTX 285, then I kind of arrived at 2 factors that a priori give some advantage or disadvantage to one architecture and the other. And I kind of split it into a compute and a memory side. And as you can see, this is all a wash. It's all about a 1, right? A little less, but a little over. But this is not meaningful, right? I mean, if you would look at these 2 processors and you would come up with something like this, then you would ask yourself, what could I gain? So, and the reason for that, to put it up front, is that our interest, or my interest, was actually what are the architectural gains of Fermi compared to the previous generation. So the next few slides, I will be giving views that has the following. One is a comparison between GTX 480 and GTX 285. And to this extent, it could be either running time or it could be frame rate. The other thing is a relative throughput. And what we mean by that is we wanted to have a metric to know how well Fermi or previous generation GPUs do when you expand the number of threads and you want to know, are we maintaining any efficiency here? If we went from 10,000 agents to 20,000, what had happened? So we got some speed up or we got some slowdown, but how is the efficiency per thread? So this is the parallelism metric that we are after. And the other aspect is that we give also, we compare ourselves, and this is primarily GTX 480, to a CPU, and this is a high-powered CPU. Now, in the following slides, I have put the versus CPU slides in backup slides, and at the end of the talk, if you find it useful, I can present it, but I didn't want to overwhelm you too much. Now, the table on the side really highlights what is the most important thing that Fermi brings to the table when it comes to AI. And this is L1, L2, and the other thing is being able to parallelize more. And this is parallelize more threads per CTA and running kernels in parallel. So the first set of experiments was on roadmap construction. And here what we did is that we took 3 configuration spaces. And you can see on the left side the complexity that is in the form of number of vertices and faces. So the first stage, if you recall, we discretized the mesh into a binary grid. And for this, we ran a grid kernel or a voxelized kernel that we fork however many faces are in the configuration space. So these are the number of threads. And then you can also see the closure for any of those configuration spaces. Then when we go to medial access transform and distance transform, and I'll call them MAT and DT moving on, then you can see how many threads do we run when it comes to DT and MAT. And definitely what you can see here is that when it comes to MAT, we exercise even hundreds, thousands of threads. And is that any viable or not? Because we definitely exceeded the 24,000 and some that Fermi can essentially take as an in-flight thread, right? Does it make any sense? And at the end of the day, I'm also showing the graph that got produced, and you can see how compact it is, especially when we compare it to the initial resolution of the configuration space. Now, granted, those graphs, they are not optimal by all means. I mean, and I'll talk about it a little later. And I think that we need to optimize them more. But nonetheless, it gives you a criteria of how much we gained by doing this representation reduction, essentially. So here you can see a comparison between GTX 285 and GTX 480. And you can see that constantly GTX 480 is kind of keeping almost the pace in any of the configuration or level meshes that we use. And we get up to a little over 2x in terms of performance. Next, we wanted to understand the threads throughput that I mentioned to you. And in this case, we wanted to look at the medial access transform. I mean, note that every stage in the roadmap construction has different level of parallelism. So this would be difficult to do. So we picked only one. And one thing that you can see that we still go linear, irrespective on the number of threads. And this is with so many threads as well. So the next set of experiments has to do with path searching. And in this case, we have picked a graph that is complex, or it has over 5,000 nodes. So this is fairly complex graph. And we have exercised 1K to 64 path queries, which we run A* in this case. And one thing to remember this, in this benchmark, all the start and goals position of the agents have been completely randomized, so there is no whatsoever correlation in a CTA between threads. And here you can see, so in this case, I try to mark when lower is better or higher is better. So in this case, on the right side, it's the speed up, so the higher is better, and running time is obviously the lower is better. And one thing that you can see here is that the GTX 285, once we get to a certain point, there is a diminishing return of how much added performance you get. But you can see that on GTX 480, obviously it gets shallower compared to where this has started, but still there is room to grow. And now this also manifests itself on the thread throughput. As you can see, it goes very steep high. And by the way, everything is normalized to the first data point here. So you can see that it goes fairly steep initially, but then at the end, it starts to go fairly shallow. It has room to grow, but not as much as before. On the multi-agent simulation experiments, so we took a data set, which is the evacuation, and we let the roadmap and the number of obstacles be constant, and we augmented the number of agents from 500 to 20,000. And this is flat level parallelism, so every agent constitutes the threads on the hardware. And we ran those simulation sessions for 1,200 frames to get the performance. So here, what you see, and so this is frame rate, and we have to be a little careful about it. The fact, you know, that the two graphs kind of get closer to each other doesn't necessarily suggest that there is no performance payoff, the other way around. So we have to be a little careful about it, because this is a frame rate. But you can see that the speed up that we get here is very close to 1.6x. And the other important thing is that on GTX 480, given 10,000 of agents, we get something that is a little higher than 20 frames per second. So eventually, this is something that will get us to a point where we can be interactive. Now when we look at a thread throughput, then you see that there is something behind the scenes. So at a given certain point, probably as we go from 5,000 and over, then it remains fairly flat, which says that these actually workloads, they were hitting something else than computational, and this is being memory bound. So this is the nature of things. Finally, on the results, and this is something that I truly wanted to get across, and I don't know if many people are aware of it or not. But this is something that demonstrates what is your choices to distribute parallelism on the GPU. So in this case, this is a workload that has only 400 threads, and the footprint is fully loaded in L2, so it's fairly sterilized and optimized in this case. Once you loaded it, it's always on chip. And now, so what are your choices? Your choices then is to say, you know what, I want to run all those 400 threads on one SM. Is that something that you would do right away? You would think so, right? I mean, because that will make the SM very efficient, right? You can hide mathematical latency and hopefully even some memory latency if you would execute mathematical instructions out of order, right? Which you can do. But there is one thing that we are missing in that, if we only do that. And the one thing that we are missing, the more we spread those warps across SMs, then suddenly we get a multiplication factor on L1 or either shared memory, and in some cases also registers. So what this graph actually shows is that if I took this workload and I spread it such that it'll run one warp per SM on GTX 480, I got a 3.3x improvement in performance as opposed to moving all the warps, all the threads on one SM. So the message here is that always seek to distribute load on all SMs first, and then optimize per SM. So obviously, our current implementation has some limitation. And like, for example, I mentioned the stack that is fairly large when we do the flat fill. And this is something that forces us actually to do multipass of the kernel on the GPU. Now, initially, I was under the impression that this would be something that will cost us. But it turns out that with the asynchronous way of launching a kernel, this is not as bad. So the one thing that is distracting here is that as a programmer, I really don't want to get into a situation where I run my algorithm and suddenly I have to break it out because something like a resource doesn't fit. Now, with respect to A-star, and I didn't talk about it in detail, A-star is I/O limited at cases. And this is when you try to copy the working set from host to device, or you want to get the waypoints from device to host. So this is something that we better address. Now, I mentioned the single-threaded hash build, and this is something that is a limitation. Right now, some measurements of us shown that there is up to 27% of frame time that is being used on the hash table build, and that's not ideal. Finally, I wanted to talk about the fact that, that within a CTA, or within a thread block, threads, there might be a load imbalance because threads might not be doing the same work. So some agent could get to their goal prior to others, and once they get to their goal, they stay idle. Then there is very little for them to do. But it's very difficult for them to avoid it. So to exemplify that, if you look at this clip, what is happening here, so you can see that the top agents actually arrive at their goals much quicker than the ones below. Now, they are all running in the same warp. So obviously, and if you scale this up to something that is much more intense in the number of agents, then obviously this is something to be concerned with. Now, just one more aspect on that. The bluish object here is actually a dynamic obstacle. So this is an obstacle that moves without any awareness of its surrounding. I mean, it has a velocity, and it goes like this. It doesn't care about anything. But agents on the side have to be careful about it. So just to recap the performance, I truly only wanted you to get attention to the second row here, which talks about the architectural gains of Fermi. And as you can see, and if you recall, when I showed any advantage on compute and memory, this was all a wash within the previous generation. But see what is happening here. On roadmap construction, we get about 90%, and we get about 40 and 47% on the other stages of our work. So some future work. I mean, one limitation with the velocity obstacle is that it's not a truly 3D. And preferably, you want to have it as being a 3D. As I mentioned, the graphs that we generate, they are not optimal, and we would have to do something to optimize it. We want to look at some more complex behaviors like flocking and others. We may want to consider parallel hash build. And there is also this zero copy that has been now published with latest Cuda, and maybe this is something useful for A-star. So to summarize, I think I've presented something that the GPU is very good at. It's multi-agent is a good framework, and it has a growth factor, and it affects many areas that we would want to look into. Now, obviously, I also talked about Fermi, and you have seen the speed up here. Finally, I want to show a clip that shows 1,000 agents that are escaping an office floor building and through 2 narrow gates. And as you can see, what is happening here, they're all bundles around those exits. and they have to constantly adjust their velocity and to wait and wait. So this is what is happening here. Okay, thank you very much, and I can open it for questions if this is necessary.
For more, please visit us at stanford.edu.